Okay, this is the last lecture in Accounting 212, and this lecture is on Chapter 13, Capital Budgeting. Capital budgeting is simply long-term planning for big acquisitions. Like at this college, capital budgeting would be when they plan on building a new sports field, or when they plan on building a new building, or when they plan on replacing all the kitchen equipment in any of the kitchens, or renovating a dorm, or buying a new 4 or 5 buses, for the sports teams. Capital budgeting would be buying all kinds of new chairs or desks or data video projectors. They usually plan years ahead to try and make those acquisitions. The acquisitions are very important. Even at this college, they're very important because without them, you would find yourself sitting in a classroom that you felt was dilapidated, out of date, poor equipment. You would actually feel like you weren't getting your money's worth and that you were in an institution that was in a state of decline. So capital budgeting, almost all companies do it, all good companies. I would say, there may be other companies that are lucky that don't do it, but before we get into capital budgeting, one of the reasons we're going to have to go study the time value of money is because capital budgeting takes place over many years. You don't just buy a building and say that's it. You buy a building, but the building then provides you with revenues over maybe 40 or 50 years. Now you may be saying, what do you mean it provides me with revenues? This college gets an incredible amount of revenue through room and board. I would say it's probably the second biggest money maker on this campus. Probably first is tuition, and second is room and board. Somebody like John Deere, when they build a building, they make money off that building for years because they use the building to build tractors, and the tractors provide a source of revenue. So all these capital budgeting decisions, again, are not going to take place in just 1 year. They usually span decades, or sometimes 4 or 5 decades. The problem with that is that money is not stable. It is not a stable, a cash flow that occurs in 10 years is not the same thing as a cash flow that occurs now. In other words, if somebody said to you, I'll give you $1,000 now, or I'll give you $1,000 in 10 years, I think all of you would say, I want the $1,000 now. There must be something better about $1,000 now, because I can guarantee you $1,000 in the future is crummy. Take the $1,000 now. Way better investment, but we are just a way better choice. But we have to go back and have a preliminary discussion about the time value of money and why is money, again, not a stable measurement, and it isn't. Let's first of all just take, I don't know if I want to begin with an interest rate. Well, yeah, let's begin with an interest rate. We all know that, again, in our society, if you put money in a bank, they'll pay you interest. But why will they pay you interest? They'll pay you to just simply give you your money, and then they'll give it back to you anytime you want. It seems odd, but it isn't odd if you really look at the facts of what's going on. Let's say that you go to a bank, and the bank says, I'll give you 7% if you'll put your money in my bank for a year or two. What's in 7%? Why would the bank give you 7%? The bank will do it, first of all, because of inflation. In other words, if you give them the money for a year, when they give you $1,000, and by the way, let's say it's $1,000, when they give you the $1,000 back, you can't go out and buy $1,000 worth of merchandise that you could a year ago. In fact, if you take $1,000 and go to the grocery store today and go buy $1,000 worth of groceries, and then you wait 10 years and try and take $1,000 and buy the same groceries, you won't be able to buy nearly as much groceries. In fact, you'll probably only get about $600 worth of today's dollars in groceries. In other words, you'll be very short. You won't get nearly as many groceries. A silly but example of inflation is when I was a little boy, you could buy a gumball that was about that big, and you could buy that for a nickel. And now, that same gumball at many places costs a quarter. In many places, it even costs 50 cents. There's been no technological improvements in that gumball. It's just a ball of, some kind of goo with sugar in it. But I still like it. But anyway, my point is there's been no technological innovations like a car, and yet that gumball costs 5 times as much. Or let me put it to you a different way. If you went, I could buy a gumball when I was a little boy, and now I could only buy 1/5 of a gumball with a nickel. I can only get 20% with the same nickel. I can only get 20% of a gumball. That shows you there's been no technological increase. We have something called inflation. Inflation results in you might have $1,000, but they will not buy the same amount of goods that you used to be able to buy in previous years gone by. Now, that's what's in an inflation rate. The bank is going to compensate you because you don't have that money to spend right away. When they give it back to you, those dollars, they have to compensate you for inflation. Another factor is there is always risk. We know that on average, it depends on the company, but if you invest in 100 different projects in 100 different banks, there's a reasonable chance that one of those banks will go under or one of your investments will fail. So we can say that, again, if you invest in well, let's actually change that. If you invest in 100 different projects, 4 or 5 of those projects will fail. That means there's a risk on all your money of about 4 or 5%. That's a very general example. But there's about 4 or 5% of the time you lose your money. Well, that is exactly the same concept when you go out and invest in any bank. If you invest in 100 different banks, you may very well lose your money or in 100 different investments. So we have to recognize that, again, that there's a 96% chance on any dollar you invest that you'll get it back, but there's about a 4% risk that you won't. And that's a very true fact. That's not a guess. Again, in some industries, it may be that the risk is 20 or 30% because they're very high-risk industries. Something like maybe drilling for oil or oil exploration. Or again, trying to open a new store to compete with Walmart. That might be a huge risk that you'd never get your money back. Anyway, they put in a risk factor and an interest rate of about 4%. And then, believe it or not, they'll also put in a 1% factor. In other words, you'll never, on average, you'll never get this money back unless they pay you for it. If you give someone your money, you will, and again, even if they give you back the same money, you'll lose 2%. If you give someone your money and they give you back the same money, you'll lose 4% because 4% of the time, out of 100%, you'll lose your money. That person won't pay you back. They'll default. Then if you said, well, hold it, let's pretend the world is perfect. Even if the world is perfect, you still want 1%. Why would you want 1%? Because money is very handy. In other words, it's the handiest of all handy things. If you said, well, I rent out shovels, equipment, but the thing that's more handy than shovels or equipment at a rent hall is money. Because money can buy you any shovel or wheelbarrow or it can, an air compressor, whatever you want to go rent, you can get it with money. So money has a risk-free rate. Just the simple you deserve that. And you can get 1% just about anywhere. You can get on U.S. savings bonds, you can get in any bank. So no matter what you invest in, you would say, I want at least a 1%, the risk-free rate. Now all these can change. Inflation can go to 3%. Risk can go to 10% or 20%. And the risk-free rate can become that money is harder to get. So again, the risk-free rate might be 4 or 5%. So an interest rate can go up or down. But those are the main components in an interest rate. And I want you to think that, again, if I were to say to you, you're a college student, I said every year, at the end of your freshman year, I'll give you $1,000 if you succeed, make it through your freshman year. This is your sophomore year, and I'll give you another $1,000. So this is your freshman, sophomore, junior, senior. I'll give you $1,000. I'm not going to give you $4,000 if I just give you that. You're going to end up with probably about $3,100 and $200 in today's terms. In other words, had I given you $4,000 here, and you went to the grocery store, you could have bought $4,000 worth of groceries. But if you wait till out here and you save all these, and you don't earn interest, you will have just enough, you will have $4,000, but you won't be able to go buy $4,000 of your freshman year groceries. The groceries will have gone up. Also, let me tell you something, there may be the risk that I, as your father, I go broke, so I never give you the $1,000 every year. I just go broke, or I die, or again, you and I have a falling out, so I never give you the money. There's always that risk. So that's the risk you never get the money. Even if there's no inflation and no risk, again, there's always a 1 to 2, 3% return on money because of its handiness. Money is it's very liquid, it's very flexible. You can do anything you want with it. It's the most flexible of all assets. Anyway, this is why a future dollar is not worth nearly as much as a present dollar. And that's critical to capital budgeting because all companies usually do what's called discounting. They simply say, if we're going to build a building now, we need to know what cash flows will come in the future, and we have to take those cash flows and strip away this 7%. On general, we'll lose 2% on every one of these dollars to inflation. We'll lose 4%. Sometimes on some of our buildings, we don't make money back. We lose money. 4% of the time that happens, so we're going to strip that out. And we're going to strip out 1% because we could get that anywhere. Once we strip that money out, we'll compare these outflows with what these inflows, these are dollars coming in, with what we spent on that project. That's what capital budgeting is. Take what you spend compared to what you're going to bring in. Again, we're outflows versus inflows. And when we take those these future outflows, we're going to discount them back using an interest rate. Now, most companies actually have an interest rate. Most companies that I've worked for, it's 10, 12, 14, sometimes 16%. And it's because this is very big. They're taking a big risk. This is usually the biggest factor in all of it. Sure, there's inflation, and they can go out and get that, and they can get the risk-free rate. Usually they can get the risk-free rate on just what a U.S. Treasury bond is paying. That's pretty close to a risk-free rate. Yeah, there's some other factors in that Treasury bond. But anyway, the point is this can be much greater, so this interest rate. So they might strip away a great deal because it could be that, again, a company is used to failing 20% of the time. What if 20% of their investments, they get nothing back? They go completely bad. Well, then they've got to put in a 20% risk factor and strip out 20% on any given project. They have to take that because that's what they expect to lose. There's an average chance that they'll lose that on any one of their investments. So when we bring these dollars back, we'll compare them to today's dollars and see if we're making a good investment. Again, every company I've worked for, and I do mean everyone, and when I worked at a public accounting firm, we helped companies do this. This is very standard, accepted theory. In fact, I don't even know if I'd call it theory. It's simply a representation of the world we're in. It's a fact. I mean, it's a bit like air. I mean, we know it's around us, but it's kind of hard to see. We just know we've discovered that we breathe it. Well, this is a bit like that in that it really is considered fact in our society, not theory. All right, with that, we're going to start working some problems. But under the problems, we're going to have to look at we're going to look at various methodologies to take into account the time value of money when we're budgeting capital. Okay, that's enough for the prelude. This is the first exercise. Again, we're in 212. This is chapter 13. We're going to be working exercise 13.1. It's on page 659. And this is about a method called payback. Payback is crummy. I've never used it, to tell you the truth. I've worked, a lot of different companies over the years, and I'm not saying I wouldn't use it. It's an easy method to use, but your author contends that there are companies that use it, so we are going to cover it. Almost all capital budgeting books go over it. I would say that if I was working for a client, I probably, I might say, would you like me to do payback? But the methods that I always used were internal rate of return, net present value. There was another one called modified internal rate of return. And there was one that we did use. It was called present value payback. And that was a little different. But anyway, we're going to do this one. I'll tell you what, it has two major flaws. One, it doesn't take into account. There's no time value of money in it. It just pretends that all dollars are worth the same, which is completely an erroneous premise. And then two, it ignores future dollars. Now you might say, well, that sounds kind of the same, but I'm saying to you that even though not only does it ignore the time value of dollars, but it just completely ignores some dollars. So it has two huge flaws. But that's not to say that something that has huge flaws doesn't have some redeeming characteristics. But anyway, payback, the premise is just how long will it take you to get your money back? So you see that again, some companies might want to know that. And this one, we begin with a year. This is a 10-year project, goes down through the year 10. This is an investment. In year 1, we're going to spend, this is what we're going to spend, $15,000. And this is negative, we're spending that. This is $8,000, and we're spending that in year 2. And then these are all our cash inflows. Again, let's say this is a donut machine. This is a donut machine, and you might say this is the donut machine, and this is all the ingredients and tools that need to go with it. You might say, well, hold on, all you need is a donut machine. But you might have to buy $7,000 or $8,000 worth of all the, think about making donuts. You're going to need dozens and dozens of different ingredients, and you're going to need also things like milk and sugar, and you're going to need coffee for a donut shop, and creamers. Anyway, that's all what we call this working capital. So let's say this is a donut machine. This is a donut machine, and we're going to call this working capital. That's the amount of money that we're going to have to put into, again, like I said, all the ingredients, the flour, the sugar, the salt, I don't know if they put in pepper in donuts, it doesn't seem likely, but anyway, and then we're going to also have to have coffee, we're going to have cups, all kinds of things, again, to support the donut machine, to actually offer the donuts. And they call that working capital because these things usually, you need to, again, use your current assets. You buy it. By the way, usually you'll get that money back because when you finally get rid of the donut machine, you'll sell off all the ingredients, all the cups and forks, and you'll sell off all the coffee and get it back. Anyway, these are all positive cash flows. And it says again, 1, determine the payback period of the investment. By the way, this is not called payback. I would call this is actually technically, I would call this uneven payback. You realize if they just said each one of these was $3,000 a year. Well, we could just take, by the way, we're spending what, $23,000. That's what we're spending. We could take 23 and let's say every year you get 4. Just divide 4 into 23 and you get how long it'll take you to pay back. If every year we got 4, but we don't. This is uneven. We have uneven cash flows. So I'm going to do this a little different. I'm just going to put an extra row here, C-U-M-U-L-A-T-I-V-E. I'm going to call this cumulative cash, and I'm just going to see how long it takes me to get to 23,000. In my first year, do you see I get 1,000? Then in my second year, I get 2. But 2 plus 1 is 3. See my cumulative amount. Then 3 plus 2, 5 is 5, 5. 5, 5 plus 4 is 9, 5. Again, this is the, you see, I'm just trying to add up how many years is it going to take me to get to this number. Then in year 5, 9, 5 plus 5, that's 14,500. And 14,000 plus 6, that's 20,500. And then 20,000 plus 5 is 25,500. By the way, do you guys see? Now I've gotten enough money. This machine will pay back somewhere in year 7. So I know it's between year 6 and 7. But you can see that that's more money than I need. So I would simply do this. I would say, all right, to finish this out, I'd say, I know that I need, you guys see, I need 6 years. Because I'll have 20,000. I need 6 full years. So 6 years plus, now what do I need in the 7th year? Well, in the 7th year, again, think about this, I want to get $23,000. And I've already got 20,000, you see? This is my 6th year, this is my 7th year. In my 6th year, I have 20,500. Now, do you see what I'm calculating here? I need how much more money? I've got 6 full years, but in my 7th year, I've got 23 that I need, and I've got 20,500 by my 6th year. So I need $2,500. And how much money will I get in the 7th year? I'll get 5,000. So if I get 5,000 in the 7th year and I need 2,500, it's going to take me, do you see, 1/2 year. In other words, this is going to do like this. I need 6 years plus I need $2,500 more, and in that year I'm going to get $5,000. So this will be equal to 6, this is half, so this will be 6.5 years. 6.5 years is payback, and that is the answer. That is the answer to number 1. Number 1, 6.5 years. By the way, let me see here. It says, would the payback period be affected if the cash flow in the last year were several times as large? Well, let's change it. Let's go down here to the last year, and let's just change that. Let's say, all right, let's not make it 2, let's make this 6,000. Even if this is several times as large, does it affect any of these? No. No, so the answer to this is, would the payback period be affected? And your answer would be, the payback period is not affected by cash flows beyond payback. Let's take a look at this and just see if we understand it. Do you see how this method's flawed? One, this method assumes that there is no time value of money. It assumes that these dollars that we're spending early are, again, equal to the dollars that we get later, and that's wrong. Also, do you guys see that this method tells you it's going to take me 6.5 years to get my money back? But it doesn't show you that you're going to get 5,000 and 4,000 and 3,000 and then maybe 6,000. It doesn't, it completely ignores this. That's what the author is trying to bring your attention to. Would the payback period be affected? No, it doesn't look any better at all. By the way, what if these were all 0? Do you see again, this would be the, let's just make them all 0. 0, 0, 0, 0. What if they're all 0? Well, the answer is still, whoops, don't make that one 0. But let's make all these 0. Again, if we make all these zeros, it doesn't affect the 6.5 years. So you see that these are being ignored. That's what I mean when I say it ignores many future cash flows. The cash flows that it ignores are the cash flows that are beyond payback. I don't know why I put that in there. That's not the way you spell payback, but just ignore that A. It ignores many future dollars. It ignores cash flows beyond payback. In this case, payback is 6.5. After 6.5, it ignores these cash flows. So this is a very flawed method. So would the payback period be affected? The payback period is not affected by cash flows beyond payback. That's the answer to part 2. And I thought I was going to do something else on this. Payback. No, that's all I was going to do. One more, okay, that's enough. We're done with this one. This is an introduction. Payback's an inferior method. But that doesn't mean it's not simple and worth looking at. I mean, you might want to look and, payback does reveal. Do you see, again, knowledge is knowledge. It does show you some attributes of this investment. So it's worth looking at. It's not one of the more powerful methods. Okay, this is the second exercise. Again, we're in 212 Accounting, Capital Budgeting, Chapter 13. We're going to work exercise 13.2. It's on page 659. This is on a very, very popular method, the most powerful, most popular method that's used today in capital budgeting, net present value. Most companies never call it that. They just call it NPV. But again, exercise 13.2 will take us through the most basic example of net present value. We got 2 requirements, but let's just read it. The management of Kunkel Company is considering the purchase of $27,000. All right, let's just jot that down. That's $27,000 they're spending. With me? And they're going to spend that money now. a machine that would reduce operating costs by $7,000. This is a future flow. This is future dollars. And this is a plus. So this is a future, would reduce operating costs per year. So these are future dollars. These are what you're hoping. This is for sure. I guarantee you right now, this money is absolutely for sure. This money will be gone if you spend it. At the end of the machine's 5-year useful life, it will have a 0 salvage value. The company's required rate of return is 12%. So in this case, this company is looking at 12%. Let's just say again their 12% has in it, I don't know, let's say there's a 4% of, let's say, inflation. Let's say there's 6% of risk, and that means there's a 2% risk-free rate. Risk-free rate. Okay, is that 6, 10, 12? So that's what that consists of. Now think about that. What we're saying is, these dollars, there is what? There is about a cumulative 12% chance you're never going to get those dollars. Or those dollars, again, they're not, you're going to lose that kind of money no matter, in other words, on average, 6% of the time, you'll never get those future dollars. When you invest in an investment, that's your risk. 4% of those dollars you'll never get back because you'll lose it in purchasing power. And 2%, well, you could get that in any investment. So you want that. You're actually going to take it out because you're going to say, I can get that anywhere. So you're going to strip 12% out of these future dollars. Because again, you're not going to get those. Or you're really saying, again, take it out so I can compare them to today's dollars. By the way, it doesn't strip it out evenly. In other words, let's jot down what's happening here. Again, we're going to spend, let's take a look. Now, right now, we're going to spend $27,000. That's going to happen now. And then we've got year 1, 2, 3, 4, 5, 6. And this is 6 at the end of the machine's, 5-year useful life. Take that out. All right, what's going to happen? In year 1, we're going to get $7,000 positive. $7,000 in year 2. $7,000 here, $7,000 here, and $7,000. Now just looking at that, 1, 2, 3, 4, 5, so that's equal to $35,000. Let's just do a test right now. If I walked up to you and I said, I'll tell you what, let's say I'm your father, and I say, I'll give you $27,000 now, or I'll give you $35,000 in 5 years. And let's again say I'll even give it to you in this pattern. I'll give it to you in increments. I don't care what the math is. Take the 27 and never look back. I don't care all this mumbo-jumbo theory. That is a way. You realize that I could die. Let's say I could die. I could get mad at you. I could have what? There could be a pandemic. Some kind of virus. Coronavirus could, get us all. And I might have, there could be a super volcano. Yeah, there's about 15 of those on Earth. Boom, they go off, we're all gone. You could have a gamma ray burst from some other planet. Boom, we're gone. You could have a sunburst, and it'd fry all of our systems. There's so many reasons you might never get this money. Take the 27, walk away and be happy. Best thing you ever did. But let's go ahead and apply theory to this and see. And by the way, it looks like, 35 is more than 27. No, it isn't. That 35 is probably not more than 27 because those future dollars have what? They're going to erode from inflation. There's a great risk you won't get them. And then again, you can get 2% anywhere. What do we want to do with this now? We want to do the, what does it say? Determine the net present value of the investment in the machine. And they do say do this, remember at what? At 12%. All right, to do this, let's go ahead and let's take these. This is called an annuity, and let's bring it back to its present value. We know that the number of the annuity, by the way, we don't have to do anything with the 27. The 27 number is just fine the way it is. It's just fine. It's now, so that number doesn't need to be manipulated. That dollar, it'll buy you whatever it'll buy you today. But in the number of periods is 5. The interest rate in this case is going to be 12%. And we need This is an annuity. And this is going to be, we need a present value of annuity factor. Now, I am going to have to change this. I'm going to have to go ahead and show you a factor table. I will tell you in real life, when I worked in practice, we never use factor tables. That is considered college child's play. You use formulas. You use formulas and use Excel. You'd never use these tables, but it's a good starting point. Let's use the tables. By the way, there's a formula behind this. There is a mathematical formula that will go in, and it will take 12% out of each one of these. Now, by the way, don't think the math is so simple that it will just go remove 12% evenly. It's going to remove 12% from this one once. It's going to remove 12% from this one twice. It's going to remove 12% from this one 3 times. You know, it's going to, do you see again, there's a compounding effect. In other words, there's much more risk 5 years out. There's a good chance if I'm your dad, I'll give you this one. But when the period becomes longer, the risk becomes greater. That again, and by the way, inflation is greater. Inflation compounds. So again, each one of these, the math isn't so simple that you're going to say, I'll just go multiply this by, and take 12% out. No, it won't work, because you have to take into account the compounding. The fact that this one is way worse. This is your best cash flow, because it's so close by. But this is going to compound twice. It's going to devalue twice by inflation. This will devalue 5 times. So the formula will take that into account when we go look that up. And I'm going to go set that up just briefly on a note. All right, I'm going to do an extreme close-up so you can see this table. Extreme close-up. Okay. Now, what we said was we really need the factor, and a factor is really not a, it's this formula. I don't know if you can see this up here, but the present value of an annuity is a formula. There's a formula that, again, compounds these periods, takes into account these interest rates, and discounts them back. And that's really, when you get into real life someday, that's what you'll use. You'll use a formula. You won't get out your little book of tables. Oh, let me look at my little book of tables. You're not going to do that. That's beneath you. But this is where you're going to begin with your education. And anyway, in this, it's the present value of an annuity. That's what we've got. Do you see the annuity? I left these up here. It's in arrears. Arrears means at the end of the year. Think of your arrear. If it's an annuity due, it's the forward part of you. Think of that. An annuity, this means the cash flow occurs at the end of the year. Arrears. If it's annuity due, it occurs at the beginning of the year. All right, we're going to go down here, 5 years. Again, we said 5 periods, 12%. Let's go over to 12%, and we have it right there. 3.605. So our factor is going to be, let's just draw it this way, 3.605. Is that what we said? 3.605. All right, now that we have that factor, again, you can see these are the years, and these are the interest rates. But I assure you, I've never done that. In real life, you always use your formula. You can just put it into an Excel cell. And you put that formula in a cell, and that's the way you'll really do it. But anyway, I'm going to jump back to the problem now. We're going to use this to solve it. But I will say this. Think if there was no time value of money. Let me tell you what the factor would be. 5. Because you got 1, 2, 3, 4, 5. And you'd say 5 times 7 is 35. That would be your factor. But look at the factor. It's 3.6. It's not 5. You've lost 1.4. That's the cumulative nature of all that inflation and all that risk over those years. So in other words, 3.6, it should be 5.0 if there is no such thing as inflation. You've lost about 1.4 in a multiplier, and that's due to, again, these other factors. You're going to strip that away, that future value. All right, let me jump back to, again, the problem. All right, let me push this back just a little bit. All right, here we're back to having the problem up here. And remember, we're investing $27,000 machine that's going to save us $7,000 a year. Well, here's the now cash outflow, and that's going to be 27,000. And then, so that's our cash outflow. Now let's look at this is the present value of the cash inflows. And that's going to be 3.605 times the annuity, $7,000. And I don't know what that is, but we'll do it right now. 3.605 times $7,000 is equal to $25,235. Add those two up, and you get $1,765. And this is your net present value. And that is negative. What's that mean? Well, I don't know if the book explains it that great or not. I can't remember. Most of the time they don't. Let me say it to you in several ways. First of all, would you automatically say this is bad? Well, yeah, but not that bad. What it means is you're not going to get 12%. Let me put it to you a different way. Let me put it to a way that might be clear. You go to the bank and you borrow the $27,000. You borrow that money. And the banker says, I want you to pay me back, and I want you to pay me 12% interest. You will not be able to do that. You will not be able to borrow $27,000 and pay back 12%. You will default on the loan. If you said to me, are you going to default on the principal or on the interest? It doesn't matter to a banker. If you don't make the interest or the principal payments, you're defaulting on the loan. Now, does it mean that if the banker said, you know what, I'll lower your interest rate to 10 or 8 or 9, you may very well be close enough. In other words, this just tells you this investment is not going to provide a 12% return. It will not, again, do what? It will not allow you to have 4% inflation, compensate you for the risk, and compensate you for the risk-free rate. It will not do that. But now, what if we went back and did this whole thing again at 10%? At 10%, this may come out positive, because do you see, you'd be stripping away a lower amount of interest. Your risk would be less. So it may be that this would have a positive net present value at 10%. But it certainly doesn't at 12. If your company demands a 12% net present value, this simply does not do it. Now let's also look at the overall. What is net present value? Net present value is when you take the present value of the cash outflows, the negatives, and compare them with the present value of the cash inflows, and see, and you do that at a certain rate. In this case, the rate is 12%. And you determine that, and by the way, these are now considered equivalent dollars. These have been compensated for in time. So now these dollars are at the same, these are the present value. These are the dollars today, the value of the dollars today. So now we can compare and subtract them and say, in today's dollars, we will not, this is not a 12% return. So that's what net present value is. By the way, there's something you should know of the test. If you do 27 here and it comes out 27 here and you come out with 0, not only is 0 the net present value, but whenever you get a 0, that's also called the internal rate of return. When the present value of the cash inflows and the present value of the cash outflows exactly equate and negate each other to 0, that's called the internal rate of return, and that's considered the inherent return on that investment. It's exactly the interest rate that you will make exactly the right amount of money, again, to compensate you for that cash outflow you're spending. All right, what's the second part of this? This, by the way, is 1. This is 1. What's 2? What is the difference between the total undiscounted cash flows and over the entire life of the machine? Well, we can do that. That's not too bad. Let's just do 2. You're going to spend 27, and you're going to get 35,000. So that's going to be 27, that's going to be 8,000. By the way, that's positive. I know you're saying 27 minus 35 is negative, but we really could do it this way. Let's change it. We got $35,000 of cash coming in. Whoops, don't we? Yeah. You know, what, 7, 14, count them all up, you got 35. The 35 is the positive, the 27 is the negative. We're going to spend 27. It's a positive 8. Do you see again, without the net present value, you would be lured into saying, oh, this is a great deal, we're going to make 8,000, but you're not. That 8,000 is very risky. You may never get it, or you may get less of it. If you do get it, it might be that there's incredible inflation. Even if you do get it, you can get a similar, smaller return that's no risk. So when you take into account all those factors, that 8,000, it's not really 8,000. It's something less. Okay, we're done with this problem. I think that's all we need to do, and we'll go on to the next one. I wanted to do one more thing with this. Let's make a third requirement. Third, do payback. Let's do a third requirement. Do payback. Let's just do payback. So it's so easy. Let's do 3. This was number 1. This was the answer to number 2. Number 2, the answer was 8,000. Let's put 3. I don't know. I can put it over here. 3. Here's payback. What did it cost you to buy this thing? $27,000. What do you get every year? 7. Just divided by 7. Now, I don't know what that's going to be. 4 times 7 is 28. It's going to be 3 point something. 3.86. The reason I want to do that is I'm almost sure I'm going to put a simple one like that in multiple choice on the exam. I'll give you one where I say, hey, you're going to spend 27, you're going to get even cash flows. This is called even payback, simple payback. The first exercise we did was uneven payback. And by the way, there is really a good payback method. It's called discounted cash flow payback. But you could learn that in a higher level finance or a higher level accounting course. So there is a good method of payback. We're just not getting into it. Okay, we're starting on exercise 3, 13.3. This is exercise, I think it's on page 660, and this is on the internal rate of return. Internal rate of return. And again, I would get used to abbreviating these. They just call that ERR. It's a bit like being a sailor. Swab the decks, right? Yeah. Internal rate of return. Anyway, as usual, my display, my digital video projector, it won't make things as big as I like. So anyway, I had to write, donut making machine. Help needed. Oh, help need. Part-time help. That should be needed. Needed at a cost savings to produced. Anyway, these are close enough. Anyway, what is this? This is a donut shop. Okay? It's investigating the purchase of a new $18,600 donut machine. So $18,600 is what they're going to spend. They're going to spend that now, more than likely. Donut making machine. The new machine would permit the company to reduce the amount of part-time help at a cost savings of 38. That's a future number. They think they can save $3,800 per year. You see, that's future. In addition, the new machine would allow the company to produce one new style of donut that results in the sale. This looks like positive too. You're going to sell 1,000 dozen more donuts each year. The company realizes a contribution margin of $1.20. Let's just do the math on that right now. $1.20 times 1,000 a year. I think that's going to be $1,200, isn't it? Move that, what is it, $1.20? 1, 2, 3. Yeah, $1,200. That's going to be more sales per year. So that's future too. So this is a future amount. This is a future. Do you see why there's risk? That you're going to spend now. That's for sure real money. These you're guessing. You think, oh, maybe I'll get this. 1,200 and 3,800. All right, what's the first requirement? Oh, by the way, how long? This machine has a 6-year useful life. All right, a 6-year useful life. You know, I'd kind of like to diagram this. Let's do diagramming. Let's do, again, we're going to have $18,600 now. And then in year 1 through 6, I'm going to get 38 and 12. That's 5,000, isn't it? I'll get 5,000 in year 1, 5,000 in year 2, 5,000 in year 3, 5,000 in year 4, 5,000 in year 5, and 5,000 in year 6. That's 1, 2, 3, 4, 5, 6. 6 times 5, that's $30,000. This must be a good deal. 30,000 is way more than 18,600. Again, if my father walked up to me and said, Chuck, I'll give you 18,600 now, or I'll give you 30,000 over this period, I don't care about the math, I don't care about anything. I'd take the 18,600. My dad may get mad at me in this year. My dad may go bankrupt. My dad may die in a what? A super volcano. My dad could die of what? A pandemic. Anyway, there's a lot of things that can go wrong in life. So there's a lot of future risk. And the inflation, you never know what inflation's going to do. In some countries, inflation is huge. All right, so what they ask, what would be the total annual cash inflows associated with the new machine for capital budgeting purposes? Well, I think they just want the total amount of annual cash inflows. Well, I guess we already got that. That's the 3,800 plus the $1.20 times 1,000. So that is $5,000. So that is the answer to, that's the answer to 1. Okay. What discount factor should be used to compute the new machine's internal rate of return? All right, we haven't talked that much about internal rate of return, but you remember I said the internal rate of return is, do you see that again, we're going to get these cash inflows, and this is our cash outflow. Internal rate of return just says there must be one interest rate that will do what? It is the true interest rate, the internal interest rate, the inherent interest rate that will bring back those cash flows all at that rate, and then we'll make them exactly equal to this. In other words, what interest rate will make these 6 cash flows, bring them back and make them a positive 18,600? Let's just say that that interest rate is 20%. Then this has a 20% internal rate of return. That's the inherent yield on this. That's the most it can make you. It's the most it can make. Well, you never know what's going to happen in real life, but at least on paper, that's the most it can make you. So when they say, what is the discount factor, that's what we want to know. What is the factor that would take these 6 cash flows, when we multiply times that interest rate and factor, it'll be exactly equal to 18,600. So to do that, let's do a formula, and let's do this one. I don't think I can do this one on the board. Let's do this. This is number 2. And I realize you can't see over here, so I'll change my direction here. Uh-oh. Battery's going low. Don't panic, folks. Don't panic. We'll try and get through this one, then I'll switch out the battery. What's the discount factor? Well, do you remember, you always, in the last one, we learned that you take, future cash flows, and we take them times a discount factor, and that's going to equal the present value. Well, let's just try and work out an equation that will solve for this. All right, in this case, the future cash flows are $5,000. We know them, isn't it? Yeah, $5,000. The discount factor, we don't know. Let's put that in as DF. DF slip. Equals the present value. We know what we want the present value to be. We want that factor that'll give us exactly $18,600. In real life, you don't do it this way, but this is where you're starting. You young pups. Anyway, So we know that we have $5,000 times a discount factor that equals 18.6. Really what we're saying is these are the positives. What factor will get us equal to this negative amount? Well, let's just do the math, and we'll get, again, discount factor, and we'll multiply each side by 1 over 5,000. So that'll be 18,600 divided by 5,000. By the way, don't really use the negative sign. You just want to factor. And the discount factor is going to be, I don't know what that is, 3 times 5, 3 something or other. I got a cheat sheet. 3.72. That's it. That factor will exactly, if you put that in there, 5,000 times 3.72, you'll get 18.6. Now what we know, this is the factor, but we know that this factor is associated and linked, to what? What makes this factor smaller? Remember, if there was no interest, 1, 2, 3, 4, 5, 6, this would be 6. A factor of 6, but it's a factor of 3.72. We know that, again, this factor is associated with 100%. Everything stays at 100% of its value. But this factor must be associated with an interest rate that takes it down to less than that. So it's associated or linked to an interest rate. Let's go find that interest rate, and I'll tell you how we could do it. In real life, you wouldn't do it the way we're going to do it. The way we're going to do it is clumsy and beginner. What you do is you go back and you use that formula. Remember I told you the present value of an annuity? The present value of anything is based on a formula. Well, you go back and use that formula and you solve for an unknown. But we're not going to do it that way. We're going to go back and use the tables. By the way, on the test, I'll give you the tables. Let me go back and display the tables real quick. All right, we're back in action. I put up the table. Remember, we know this is, again, the present value of an annuity. Why do we know this is an annuity? Because remember, we're getting $5,000 again and again. That's an annuity. It's an annuity in arrears. But we know that this factor, and even if you can't see me, I'm off the screen, the 3.72. Let me swing it over there for you so you can see. See, the 3.72. We know this factor. It's associated with an interest rate. So again, and by the way, this is a clumsy way to do it, but this is the way you do it in the first class you've taken. We're going to go back to this table and see if we can find the factor. Do you see all these factors? There's got to be, look, there's 3.6, that's close to it. Where can we find a 3.72? Well, let's go look for it. We'll find it, and we actually have quite a big clue. I'll tell you what the big clue is. How long is this project? We know this project is 1, 2, 3, 4, 5, 6. So let's go down to the 6th year, and let's go look for 3.72. And 3.72 is right there. Well, it isn't there. It's not perfect, but there's 3.68, 3.84. It's between these two. It's really close to 3.78. There it is. There's our answer, 15%. That is the interest rate that will yield a factor. Where did I see that 3.72? There it is. This is very close to 3.72. By the way, if you'd really gone back and done the math on this, it'd come out perfect. This is really not accurate. That's probably about 15.3%. That's what it really should be. The answer should be, but we're just beginning here. So anyway, this factor, 3.72, which is close enough, is very close to 15%. That is the internal rate of return. That interest rate will yield you that factor. We know that factor, again, will take and drive down those cash flows to exactly the $18,600, which is that's the negative cash outflow. It'll bring these back to that 18.6. That's the internal rate of return. In other words, in this project, you will not make more than 15%. That is your internal rate of return, assuming the cash flows do turn out to be fairly close in the future. If these are the cash flows you get, you're going to end up with a 15%. By the way, let me say this a different way to you. If you went out to the bank and borrowed $18,600, and the banker said to you, I'll loan you that money, but I want you to pay me back, and I want you to pay me back a 15% interest rate. You would be able to pay him back the principal and the interest, and you would have no money left over. As of today, Now you might say that'd be dumb of me, but hold it, maybe it wouldn't be. Maybe you want to be in the donut business. And by the way, this is just the money you make on the donut machine. Maybe you'd make all kinds of money on other factors. Maybe in your donut shop you'd have orange juice and coffee. And maybe you'd have not just donuts, but you'd have other things, like maybe you'd have lunch. Or maybe you have eggs and bacon, I don't know. But you still might be able to do it. Maybe this is just a bicycle shop, but they want to have donuts. So the bicycle shop says, we don't care about if we make money. We just want a donut machine in there to get people coming in the morning. So again, they still might do it. Now what if the banker said to you, I'm only going to charge you 10% on the interest? Then you'll make 5%. You'll be able to keep that money. So again, that's what this means. Now let me shut down again and go back to our problem. But that is the internal rate of return on that. All right, we're back to the problem. All right, and what did they ask? In 1, they asked us what were the cash flows, and 2, what discount factor. We did get 2, actually. 2 was this. This was the answer to 2. 3, using the exhibit as a reference, what is the new machine's internal rate of return to the nearest whole percent? This is 3. Remember, I just showed you how we got that 15%. We got that factor, and the factor was for 3.72. We looked up here and got 15%. In fact, this was the circle that we circled it with. This is also, but it no longer applies to this. So the internal rate of return is 15%. For, in addition to the data given previously, assume the machine will have a $9,125 salvage value at the end of 6 years. Let's just stop right there. If they want to assume that, then let's go ahead and modify our timeline here. They're saying out here $9,125. That's what they said. So in other words, you see, we're going to spend $18,600 on the donut machine, then we're going to get $5,000 every year. We're going to save some of that and get some of that in selling donuts. Then we're going to sell the machine out here in year 6 for $91.25. This will change the whole problem. It really does. Everything we just did in 1, 2, and 3 is no longer valid. But that's okay. I think. Anyway, what do we do here? Okay, under these conditions, what is the internal rate of return to the nearest whole percent? Hint, you may find it useful to use the net present value and find the discount rate that will cause the present value closest to 0. All right, this would take us a lot of time. Okay, let's read this last one again. It basically says again that we're going to get a $9,125 salvage value. If you were thinking about this donut machine, you see that has to make everything better? It has to. In other words, this is adding $9,000 to your cash flows. So your internal rate of return has to be bigger than that. In other words, we're saying that now you could accept even more risk. You could have even greater inflation. Do you see that that $9,000 is going to allow you to accept greater risk? Again, the internal rate of return is just the inherent, the highest interest rate that you can get to bring those cash flows back to the negative cash flow. And now we've got more positive cash flows to bring back to this negative. Well, anyway, we could simply go back and do this again. First of all, we could go back in and put in 16%, 17%, 18%. Now, I'm not going to have you do that on the test, but I did do it. And I hated doing it because it's a crummy way to do it. But I did do it. And I'll show you what I found. Let's see if I can show you. Let me go back. Yikes. Get out of this. What am I doing here? I had to be filming this. I want to go back to the camera, I guess. Yeah, there's the camera. All right, I don't really want to do this, and I'm not going to have you test it on it, but I'd like you to see it just the same. So I'll scoot that up there in case you can't see it. Super close up. Here's part 4. I went back and calculated, and remember, I was putting in 15%, then I put in 16 and 17, and what I found, by the way, I used a little different methodology, but what I found, you see, is I was always having positive. In other words, I really used net present value to do this, but each time I had a positive. I wasn't coming out, I wanted to come out with 0. I was trying to get what? Take the present value of all the cash in and subtract it from this, and I want to come out with 0. Well, I kept trying different rates, and after I got up to 22%, I got 0. And again, think about it. When I got to 22, if I go show you this, if I go back and do this problem again, and I show you the present value of the 5,000s, and then I show you the present value of the 9125, and I do it at, I don't know if you can see that very good, but that's 22%. It'll come out to be 0. Once again, let me tell you what that means. You go to a bank, and you say, banker, I want to borrow $18,600. And the banker says, well, I'm going to charge you 22% interest. You will be able to not only pay back the $18,600, but you will be able to, I don't know if you can see that, now that I've got in for that close-up. Can you? No, I cut it off. Let me say it again then. You go to the banker and say, I want to borrow $18,600. The banker says, I want 22% interest. You will be able to pay this off and, again, pay off your principal and your interest, the 22%, but you have nothing left over. That's what the 0 means. Now, what if the banker said to you, I'll loan you the money at 10%? Well, if the banker loaned you the money at 10%, then you have 12% left over for your return. So internal rate of return says it is the greatest amount you can get on this project. It is truly that interest rate which brings the present value of the cash in to the cash out. It is the inherent rate of return of this investment. So with that in mind, like I said, the answer to part 4, and I won't put a problem on the test like that, but the internal rate of return would be 22%. Now, I won't make you do the math on that, but I might put a multiple choice on the test and make you guess. Like, what if on this one I just said, will the return, again, if we have a $9,000 salvage value, will the internal rate of return go up or down? I hope you think, well, gee, that's really good. The internal rate of return has to get bigger. We'll be able to afford what? A much higher interest rate because, again, there's a much bigger cash flow there. So that's all I'll do on that. Now let's go ahead to exercise 13.4 and stop on this for now. I just wanted to film the whole solution, just in case you didn't get it. Anyway, regardless of you being able to see the background, you should have the whole solution. And you can go back and rewind or whatever to see the beginning of it. Okay, back on the ground, back on the gas. Here we go, chapter 13. Still exercise over in 212 accounting. Chapter 13, exercise 13.4, page 616. We're doing NPV again. This is a problem where, again, we've actually already done this, but we're doing a little repetition now. Just trying to increase our skill base, get a little bit better. It says Lookout Products is investigating the purchase of automated equipment. The automated equipment that will save, looks like it's going to save $400,000 a year. So that's your cash inflow, that's your guess. That's your future. That's your future value. That's the one that's so unstable. really, in a way. You just don't know for sure if you're going to get that. Each year, direct labor and inventory carrying costs. That's what it's going to say. It's going to reduce men and women, and you're not going to have to carry as much inventory because it'll probably make inventory quicker. You know, you don't have to carry as much inventory if you can make it faster and have less setup. This equipment costs $2.5 million. Ooh, that's a lot. That's a real number, and that's in today's dollars. So they say it's going to cost you $2.5 million, $400,000 each year. This is expected to have a 15-year life. All right, 15 years. That's a pretty long life. Useful life with no salvage value. The company's required to return 20%. That must mean there's a lot of risk in there. Probably, again, this machine, whatever it is, that means there's probably a great deal of uncertainty whether they'll ever get that. There are also, in 15 years, there can be a lot of inflation. There can be a lot of opportunities for things to go wrong, things to change. On all equipment purchases, management anticipates that this equipment will provide intangible benefits. I don't know what those are. Intangible benefits. Maybe it's going to make such as greater flexibility, higher quality output. That is good. Whatever they're making, that's going to reduce scrap. And again, it's going to give them the ability to produce more than whatever they used to produce. They can produce different parts with it. That will result in additional future cash inflows. Well, then really we're just doing a guess here because they say they should try and quantify those. But with what they've given, they say, what is the net present value of the piece of equipment? What is the NPV? That's what they want. What is the NPV before considering those intangible benefits? Let's do a little bit of a timeline here. We're going to spend $2.5 million, and that's going to happen now. And then we're going to bring in $400,000 in year one, $400,000 in year two, $400,000 in year three, $400,000 in year 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did I get them all? Uno, dos, tres. Da, 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 da. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. So there's our cash inflows. By the way, let's do the math. What's 400,000 times 15? That is equal, if you take 400,000 times 15 years, that's $6 million. Now, if your father came up to you and said, Chuck, would you rather have $6 million in the future or $2.5 million now? I'd say, Dad, I'll take the $2.5 million. And he'd say, don't you want to do some computations on that? You learned a lot in college. And I'd say, no, I don't care what I learned in college at all. I just want the $2.5 million, Dad. See you later. Just slap it on me. Put it in my bank account. I don't want that. Yeah, there's so many uncertainties on these. Inflation, the risk you never get it. Super volcano, meteor. Not only a meteor, it could be, what else could get you? Maybe some kind of other biological issue for the Earth. Anyway, a lot of uncertainty out there. What else? Meteor. Okay, let's keep going. Got distracted there. So now here's all the cash flows. And it says, what is the net present value? Well, again, let's do this. We know that, again, the net present value, this number is just fine. It's now. We don't need to do anything with this, but all these, this number, this is 10 years out. It's going to have 10 years of inflation compounding. You're not going to, that's not nearly worth $400,000 today. Anyway, we know this. We know that N, the number of years, is equal to 15. We know that the interest rate is equal to 20%. And we know that this is an annuity. And we know that it's actually just a normal annuity. So we've got to go out and get the factor for this. In other words, we want to get the factor for this. And whatever that factor is, let's just even we'll put the factor in here, and we're going to multiply that times $400,000. And then we'll know what's the present value of these cash inflows. So give me a second and I'll bring up that table. All right, we're going in for an extreme close-up of this table. You're going to have to use these on the test, remember that. All right, remember we said 15 years, 20%, and it's going to be compounded once a year. That means, again, that every year, that 15 times we're going to strip away the interest for this cash flow that's way out in the future. It's an annuity. What's that factor going to be? Well, let's go down. This is the present value of an annuity in arrears. Arrears means at the end of the year. Going to go down to 15 years. There's 15 years we're going to cut across, and we're going to look for 20%. That 20% is right here. We want 4.675. So let's put in 4.675. We'll take that times this $400,000. I'm going to try and jump back to my other problem. I think that's right. That's where we left off, wasn't it? No, 13.3. No, that wasn't it. We're working 13.4. Doggone it, this technology drives me nuts. There it is. No, that's 13.3. Maybe that's it. No, that's it. I don't have it. Now that is really frustrating. All right, I'll have to turn off my goddamn. All right, we're backing out again. Get a broader scope of the world. All right, remember we got this factor, 15 years, 20%, annuity, 4.675. That is the factor that, again, equates stripping away. By the way, do you see how small this factor is? Look at if there was no interest. Do you know what the factor would be? 15. 100%. 50. This factor is 4.675 because look at the power of a 20%, stripping away 20%. Interest for, again, inflation, for risk. Look what it does. It takes this from a factor of 15 years down to 4.675. You've lost almost 10 times, again, your money due to that future value. So anyway, if we multiply this out, I believe you get $1,870,000. Let me just check. I think I did that just a minute ago. Yes, I did. So now we know this is the future value of the cash inflows. Now let's write up here, this is going to be the cash outflow. And the cash outflow, you remember what it is? The cash outflow is $2.5 million. So $2.5 million. 1,860,870. Now remember, this is the negative. This is the amount you're going to spend. This is your positive. So this is going to be $630,000. And you remember what we call this? We call this the net present value, NPV. What does this mean? This means that at 20%, again, it will devalue that money so much that we will not get a 20% return on this. Now, it does, we might get a 10 or 12 or 14%, but we will not make it to 20%. If we went to a bank and borrowed $2.5 million, we could not pay back 20% interest. We would default on the loan. So this is the answer to 1. Let's put the answer to 1 up there. All right. What is the minimum dollar value? What is the minimum dollar value? Oh, this is kind of harder, per year. The minimum dollar value per year that must be provided. You know what, I don't like, well, let me write this off to the side. Okay, we're still working on exercise 13.4, but you know what I did? I didn't like the way I was getting so scattered here on the board, so I moved this over here. It was the same computation, but remember we put $2.5 million in this donut machine. Isn't it a donut machine? No, I don't know what this is. No, this is automated equipment. It's not a donut machine. But anyway, remember we got the present value, the future cash flows. It was right over there. And then the net present value was negative $630,000, which means we will not get a 20% return on this. That's this whole problem is saying this company wants 20%. Now in part 2, it says what minimum dollar value must be provided by the equipment's intangible. Remember they said there was some intangible benefits like greater flexibility and higher quality output, higher quality parts to justify $2.5 million. Well, we can answer that quite easily. It's 630. That's it. We need 630,000 to get this thing up to 20%. But the hard part of this is they say the minimum dollar value per year. Well, you know, again, you'd say the answer is $630,000, but that's in total. That's what they need. And they're saying how much do they need per year? So that means we have to go back and think about this. All these formulas, all these work off the premise that some future cash flow times a discount factor will equal, again, a present value. Well, no, this is how all these things work. They work off the similar, some kind of cash flow times a factor to bring it, to strip it of its interest, gives us a present value. Well, we do know we want $630,000, don't we? We do know that, right? That's what we want. We need that. The future cash flow, we don't know that. We do not know the future cash flow. Let's put it in there like that. What discount factor do we know that we have? Well, it has to be this one, remember? The discount factor for 15 years at 20%, and it's an annuity. They say they want to know the minimum value per year, and it has to come in over the whole year. That's what they're looking for. They want, in other words, they're saying spread this $630,000 out over the whole future of this thing. Well, the whole future is, again, this factor right here. That includes 15 years at 20%. So we can say, let's put that factor in there, 4.675. Isn't that what it is? All right, now if I go ahead and, let's again say, let me draw a line here. This is my theory. But there's my formula. If I go ahead and do the work on this, I'll get the future cash flow is equal to $630,000. And if I multiply both sides over 1 by 4.675, then I'll get the future cash flow is equal to, and I don't know what that is. I don't know what 630,000 divided by 4.675. I get $134,759, and there's a little bit of 35 cents. That is your answer. Let me see if I wrote that down in mine. I guess there's 35 cents in there. I wouldn't care if you put that on a test or not. But that is the answer to number 2, right there. In other words, what would we need? Again, 130. Now think about this. You're going to need $134,000 15 times to get today $630,000. If you take that times 10, you're going to have well over $1 million in future cash flows. It's going to take well over $1 million out in the future to get $630,000 today. So that's the answer to part 2. And let's do just a little bit more, just to get some more practice on these. Okay, we're going to do 13.5. Just a little bit more practice, but this is, again, Chapter 13, Exercise 13.5. Still on Chapter, as I said, 13, page 660. And this deals with preference ranking. We haven't hit on this yet, but what if you have, there's project A, B, C, and D, and again, when we look at this, they've already done the NPV. They have several projects. And again, they're going to spend $90,000, $100,000, $70,000, and $120,000. And here's the present value of the cash inflows. and here is the NPV. Well, how do you rank these? I mean, look at the best one. Let's look at the best. It's 40,000. This looks like the best NPV, but you do have to spend more money, do you see? Let's look at the worst one. 35, isn't it? 35 is the worst, but you don't have to invest that much money to get it. What we really need to do is maybe we should just do what? Divide NPV by investment to get a ratio. Do you see what that's going to do? It's going to tell us how many dollars we get based on how many dollars we invest. And that's a very good project profitability index. And that's what they ask us to do. So let's do it. Let's do it for A. Let's take 36,000. That's what we're going to get out of this. That's the NPV. These are all the NPVs. 36,000. Let's divide it by what we invest, 90,000. 4 times 9 is 36, so that's going to be 0.4. We get 40 cents. Every time we invest $1, we get 40 cents back. By the way, that's 40% above and beyond what you invested. Let me see. I'll talk more about that later. Here we get an NPV of 38,000. That's the net present value, and we invested 100,000. Well, that one's going to be easy. That's just 0.38. Over here, we get 35,000, and we invested 70,000. That's going to be exactly 0.5, isn't it? Yeah, 7 times 5 is 35, so that's going to be 0.5. And finally, D, we get 40,000, and we invested 120,000. Yeah, that's going to go in 3 and then 3 again. Okay, this is going to be 0.33 repeating. So, all right, this is the project profitability index. Right there, and there, and there, and there. All right, that's it. That is number 1. We are done with 1. Now, what's that tell us, though? Remember, the 36, do you see again that this really means this is above and beyond your original investment? It's saying that, again, on this investment, you'll get everything back. You'll get all of your 90,000, and then you'll get 36,000. Well, how much more is that on each investment dollar? You get 40 cents above and beyond what you invested on each dollar. Here you get 38. Every time you invest $1, you get, not only do you get your dollar back, but you get 38 cents. Here you're going to get your dollars back. You see, you can get all your dollars back, but you're going to get 50 cents above what you got. And then this one, 33. Then it asks, rank them. All right, we can rank them. Rank the proposals. Well, this one's the best, so let's do this. Really, this one's number 1, 0.5. This one is number 2. This one is number 3. B is number 3. And D is 4th. And if we were to do this, I could do it another way. I could say, well, I would rank them like this. C is in first place. Second place is A. Third place is B. And fourth place is D. So here's my rank. And this is the answer to 2. My rank is C is the most desirable because it's got the highest yield per dollar. A is the second choice, B is the third. Whoops. B is the third. Sorry about that. And D is our last choice. And that's kind of interesting because what? D had what? The greatest net present value. This is a short problem, and I thought it was worth tossing in. We're going to do 13.6 too, though. It's good practice. All right, this is 13.6, and it's kind of a repeat of what we've been working on before, but it's good practice. Oh no, this is something new. I take it back. This is a little something new. Simple rate of return. This is another inferior method, but many companies still use it. This is an inferior method because it does not look at the time value of money. It ignores the time value of money. But even though it does ignore the time value of money, it actually looks at the accounting rate of return. And the accounting rate of return is important because many times that's what shows up in financial statements. Anyway, the simple rate of return is just two numbers. You take the incremental amount you make each year, the annual, incremental means how much you're going to increase, again, how much more will you get. Annual incremental increase in accounting income, and divide it by what you paid for the investment. So it's not a very hard concept. But again, it doesn't mean that it'll be easy to get to it. Let's do this. Again, let's take a look at the problem. What do we got? The management of Ballard Microbrew is considering the purchase of an automated bottling machine. They're going to spend $120,000 on that. All right. Let's go ahead and put that up there. That's what's going out the door right now. The machine would replace an old piece of equipment. It costs $30,000 to operate. The new machine would cost $12,000 per year to operate. The old machine currently in use could be sold now for a salvage value of $40,000. Well, that's a positive number. Again, we can sell it for $40,000, so that's cash in. The new machine would have a useful life of 10 years with no salvage value. All right, this is kind of a hard one, but if we look at it this way, let's not do it in terms of cash flow, but first of all, let's go back and take a look at these numbers. It costs $12,000 a year to operate. That's the new machine costs $12,000. The old machine costs $30,000. So let's just put those two numbers together over here. $30,000 is what it costs. That's a negative, actually. That's what the old one cost to run. The new one, it will cost $12,000, and that's a negative too. But if we buy the new machine, we'll save $8,000. We will save, oh no, we'll save $18,000. We'll save $18,000 a year. That's our savings, and that's every year. Okay. So it asks, what is the annual depreciation expense? Now, normally, you never take depreciation expense into account when you're doing capital budgeting. Capital budgeting is cash flows only. But this, I told you, it was a bit of an inferior method, and so it is. It takes into account accounting numbers. Anyway, this is one of those times in life when I'd say there's more than one right. This is a time when, I'm not really saying this is an inferior method, but that doesn't mean that the information is totally invalid. It just means that it takes into account depreciation, which is not a cash flow. Some managers consider that to be valuable information. I feel like always focus on cash flows because cash is what really you're in business to make, dollars. Anyway, though, it says, first of all, let's just get to the heart of this. What's the annual incremental accounting income? Let's just draw a big line. I know they're going to ask that. Well, let's just see. First of all, the annual income, we already got it. We know we're going to save. Let's do it like this. Let's do these in negatives. We were going to spend $30,000, but now we're only going to spend $12,000. And these are negatives. So again, if we take that, that's how much we're going to save every year. What's the investment? The investment is $120,000. $120,000 is what we're going to invest. Oh, hold it though. We can sell the old machine. We can sell the old machine, sold now for sale, so we can get $40,000 for the old machine. So our initial investment in this case is going to be $80,000. We're going to save $18,000 a year, but there is another thing. That's going to be income, that's true. We're going to save $18,000 a year, but we also have to take into account that another expense that's going to go up. Do you see this new piece of machinery is going to have depreciation on it? So let's drop down here, and it does ask us in number 1, it says, what is that depreciation going to be? We'll take $120,000, and it says 10 years, no salvage value, so it's going to have no salvage value. Divide by 10, and that's equal to $12,000 a year of depreciation expense. So what we can say here is that, again, $18,000 is our savings, but we're going to lose $12,000 in depreciation. So this will be our whole equation. And if we do this again, we can get the internal rate of return. 30 minus 12 is 18. 18 minus, that's weird. Those two numbers are the same just by a fluke. I wish they wouldn't have done that. This 12 is not related to this 12. They're just by chance. Anyway, what do we got here? 30 minus 12 is 18. 18 minus 12 is 6. So our incremental income will go up 6,000. We'll save 18,000 every year, but we have depreciation of 12. So that's 6. 120 minus 40 is $80,000. There's our investment. So we're going to invest $80,000. We're going to get $6,000. Well, 10%, that's going to be about 7%. I don't know what that's going to be. Let's just see. 75%, that's going to be 7.5%. And that's going to be our simple SRR. SRR. That's our simple rate of return. So in number one, they said, what is the amount of annual depreciation expense with a new bottling machine? Well, there it is. That is number one. 2, what is the annual incremental net operating income provided by the bottling machine? The annual, let me just draw an arrow to this. It is, what is the annual net income provided by the new bottling machine? That will be the 30,000 minus the 12,000. And that's, remember, 30,000, it costs 12. So we'll save that amount. But then we got to take out the depreciation, which is another 12. So that is 30 minus 12 is 18 minus 12. That's $6,000. I think that's what they want in that second one. What is the annual incremental net operating income provided by the new bottling equipment? That's it, 6,000. So this is the answer to 2. The answer to 3. What is the amount of the initial investment? The amount of the initial investment. Well, we said we got to spend 120,000. But then we can pick up, 40. We pick up 40,000, and that means we're going to be at $80,000. That's our initial investment, and that is the answer to 3. And then 4, what is the simple rate of return? Here is 4. The answer to 4 is this whole thing right here. All of this is 4, but here is the true. There, that's 4. That's a funky 4, man. Fantastic 4 would be upset with me. That's number 4, 7.5%. So that's your simple rate of return. If you did go back, and I think I did the internal rate of return on this, and it's like 20%. So it shows you how much difference there is when you look at just cash flows. Like I said, I'm pretty sure I did the I can't remember. I didn't put it down on paper, but like I said, I went back and I said, well, what's the internal rate of return? Remember we worked that in the previous problem. Internal rate of return on this thing is about 20% because it ignores, remember, it doesn't take into account that depreciation. Again, the internal rate of return and net present value are methods that simply use cash flows. This is the only method, SRR, that takes into account depreciation. It's the only one. Try and remember that. Okay, we're going to do one more and quit. I am so delighted to say this is the last problem I'm going to work this year. Good Lord, what a long year. Still on chapter 13, we're going to work exercise 13.7 for a little bit of practice. Page 661, it's on NPV. 2 projects in this problem. Again, this is a company called, Parrot Industries. That's the name, Parrot Industries. Has $100,000 to invest. They got project A. And they got project B. Do you see each one? Oops. What's it show us there? Cost of equipment. This is going to cost us $100,000 for equipment. This one's going to cost us $100,000 in working capital. This is a good problem. I'm glad we're going to work it, even though I'm pooped. All right, so this is a little bit different. This is saying they're going to buy, in Project A, they're going to buy a new machine. They're going to put that machine out in the plant, and that machine is going to save, let's say, $21,000 on material and labor. And the salvage value, they think that in how many years? 6 years. In 6 years, they can sell that machine for $8,000. Now, this Project B is entirely different. This says that they're not going to buy new equipment, it's going to be working capital. Let me give you an example of that. Let's say you go into Walmart, and Walmart decides that they are going to start selling skis. You know, they're going to start selling skis. And again, they're going to have a whole sports shop that's really big, and they're going to sell skis, and also that's for the winter. In the summer, they're going to pick up and have a very big display of skateboards and water skis. Do you see the logic there? Summer, skateboards, water skis. Winter, they're going to pick up and sell snow skis. They think it's going to take them $100,000 to invest in the inventory. They're going to go out and buy a whole bunch of inventory. That's entirely different than buying a machine. Because let me tell you what's going to happen to that $100,000 in 6 years. They're going to get it back. Do you see that you'll have to invest $100,000, but the machine will wear out over 6 years? But they'll keep buying. This $100,000 is going to be wrapped up in skis and skateboards and water skis, snow skis and water skis. So this, when they decide that in 6 years they say, nah, we're getting out of it. We're getting out of it, and we're going to go sell, let's say again, boots. But when they do, they'll sell off those skis and get their money back. So this is called release. That will release in 6 years. Anyway, it says get the working capital. The working capital for Project B will be released at the end of 6 years. Do you see that? Released. This, again, in 6 years, we'll get that $100,000 released. In real life, it usually isn't that beautiful. You don't get all of it back. In other words, when Walmart finally decides, it's always something. Usually, many times, Walmart, when they go to sell all those skis, they'll discount them, and they might get 80 or 90. But most of the time, when you work these problems, the author just says it's the same. But the concept is there. When they, in 6 years, they'll sell the remaining skis and skateboards and water skis off or something. Compute the net present value of Project A, compute the net present value of Project B. Well, let's try and do that right down here. First of all, both of them, let's do a timeline. Both of them require 6 years. In other words, they've got, one of them is going to spend $100,000 now, and another one's going to spend $100,000 now. And then one of them is going to get 21,000, 21,000, 21,000, 21,000, 21,000, 21,000, 1, 2, 3, 4, 5, 6. And then in the last year, it's going to get an 8. And this one is going to get 16, 16, 16, 16, 16, and let me go down here a little bit, 16, and then 0 salvage value, but don't forget, you're going to get not only 16, you're going to get $100,000, and that's again called the release. Release of working capital. WC stands for, again, where does it say that? Working capital, right here, working capital. Working capital is going to, that $100,000 of working capital is going to be released. So do you see, this one gives you a nice return and then $8,000 salvage value. This one gives you a lower return, but then a huge release of working capital. And that really is true. I mean, usually when these stores carry a new line, they can always, again, leave that line and move to a new line. And when they do, they liquidate, they sell off all that stuff. So anyway, let's take a look again. Let's do it this way. We'll say now, the investment right now for this one is $100,000. And let's say the present value, let's do this. Present value. Present value. Now this one is going to be a little bit harder. We need to get a present value for the 21,000. And let's do that. Let's do it this way. The 21,000, do you see it's an annuity? It's an annuity, so we want the present value, N is equal to 6 years, I is equal to 14%. See, it's right there, 14% is what they say, right in the problem. And then this is an annuity. Now this is a little different over here. This one, again, the $8,000 that they're going to get, it also, the number of years is 6. The interest rate is 14%, but it's a one-time cash flow. So that's different. This is an annuity. This is a one-time cash flow. They only get that once. So we're going to need different factors. An annuity is very different because you're going to get 6 cash flows. This $8,000, you're going to get it once. Anyway, let's go look up some of the factors for that. Now let's do the other project too. The other project is going to take, let's do project B over here, $100,000. It's going to have a $16,000 annuity. Let's put that down, $16,000. And that's going to be the same thing. Let's draw a line to that. N is going to be equal to 6. The interest rate is going to be 14%. And it is an annuity. All right, that's the $16,000. Now let's say, what about this release of working capital? The release of working capital is going to be $100,000. And that will be, N is in 6 years, I is 14%, but it's a one-time cash flow. So let's go try and get, I wish I wouldn't have done that quite that way, but let's go try and get these factors so we can do the math. I need to go get this factor, I need to go get 4 factors. So let me put up the factor tables and let's see if we can get the net present value of those. All right, and remember, here's all the same numbers, but I'm just going to go look for those factors. I need N is equal to 6. This is an annuity, so I'm going to go get the annuity. N is equal to 6 right here, and I need 14%. So I'm going to go over and get right there, 3.889. So I'm going to take this times 3.889. All right, now I need the same factor. N is equal to 6, I is equal to this, 14%, and it's an annuity. So for this factor, I need 3.889. That's the 2 factors for the annuities. 6 years, 14% annuity. Let's go get the factors for, again, a one-time cash flow. All right, I've got a new table up, and I don't know that you've seen this one yet. And again, this, oh dear, it's the same doggone table. Grab it over more. Let's get the right one. Oh boy, I love these. All right, this is the present value of $1, not an annuity, $1. And we need N is equal to 6, 14%, but a one-time, that's $1, a one-time cash flow. So we go down to 6 years, over to 14%, and notice it's 0.456. So we need 0.456. And over here, this is 6 periods, 14%, one-time cash flow. 6 periods, 14%, one-time cash flow, 0.456. So 0.456. Now we'll go back and do all the math, and we'll be able to get the present value of both those projects. Okay, we're going to wrap up here. As I said, we've got Project A, Project B. Now again, Project A, we're going to get $21,000 every year and then sell the machine. Project B, we're going to put it in inventory. Skis, water skis, snow skis, and skateboards. but we're going to get that released. At the end of 6 years, we'll sell that off. And also, we're going to have annual cash inflows of $16,000. Remember, we got the two factors. The one factor for an annuity was 3.889. For, again, a one-time cash flow was only 0.456. Do you notice that one-time cash flows are much smaller? They're smaller because they only occur once, so they have a smaller factor. What we're really saying is a dollar received in 6 years at 14%, a dollar is only worth 45 cents. This one-time cash flow. Let's do some math here. 21,000 times 3.889 is equal to 81,669. That's a positive cash. There's your inflow, there's your negative outflow. That's the present value of all those future cash outflows. Now let's do 8,000 times that. 8,000 times 0.456. That's 3,648. That's a positive cash inflow. Let's go ahead and subtract those from 100,000. I get that this is a $14,000 negative. 14,683. Whoops. And that is a negative NPV. All right, let's do the math over here. All right, this one, we're going to take, let me see, the same factors, 3.889 and 0.456. I'm going to erase that so I have enough room here to put these in here, but that's where I'll put my math. But the $100,000, and then I'll put really, all right, it's time to wrap it up. Project B, same thing, it was an annuity, so we can use the same factor. Same factor, 3.889, so I'm going to take 16,000 times 16,000 times 16,000 times 3.889. That's going to equal $62,624. $62,624. All right, and now the 100,000 times this factor, 0.456. Well, I can just see that'll be 1, 2, 3, 4, 5. That's going to be $45,600. If I multiply 100,000 times that same factor, remember the factors here were the same. 6 years annuity. This is a 6-year 14%. It's a one-time flow. You get that back once when that project ends. So now let's say, okay, minus 100,000 equal to, then go plus 45,600. Okay, I'm going to cheat on this because my calculator's on junk. And that's going to be $7,824. And this is an NPV, this is an NPV negative, and this is an NPV positive. What does this mean? Project A will not give you a 14% return. It will not do it. In fact, you're going to be $14,000. Now, sure, Project B will not only give you a 14% return, it's positive. That actually means you'll get more than a 14% return. You'll probably get 16, 18, maybe 19% on this. The positive net present value means when this is done, let's say you went and took a 14% loan at the bank. You could pay off the bank loan. You could pay off the $100,000 back, pay off the bank loan and the interest, and you'd have $7,824 left for yourself. This is the answer to 1. And this is the answer to 1 and 2. This is the answer to 1. This is the answer to 2. 3, it says, which alternative would you take? Well, we don't know. In real life, they really might do A. There might be a compelling reason why losing money on this project fit in better with a corporation or with a company. There could be something compelling that we don't know. But given that this is all we know and that we don't know anything else compelling, we would select B. B has the positive NPV. Okay, that's it. That's all you're going to be responsible for in Chapter 13. Really, in fairness, a lot of that was repeat, but practice.